right. Good morning. How are you guys? I went to a wedding this weekend in Michigan. It was nice. It was good weather. It was kind of exhausting. Got back pretty late Sunday because of delays and stuff. But back at it. Okay, so last time we left off kind of the tail end of our granular filtration discussion. Here we worked through part A. Did you guys get an answer to part B on this one yet, or did you get that far? Didn't get that far. Okay, so why don't you take a few minutes? That'll give you a chance to fill my water bottles and stuff, and work towards part B. So just a quick overview, reminder of the problem and what we did so far. This is a conventional water treatment plant. We have a total flow there because it says this plant treats 2.4 cubic meters per second of river water. And then we've got filters, so more than one filter, of course. They're 8x8. They operate on a schedule. Gives that schedule, we had to find the total filtration time, just had to subtract the other, like the time backwashing, the time rinsing, and the time for the air purge from that 24-hour cycle to get that. And then it gives us backwash rate and a loading rate. And then part A was asking what's the filter efficiency. And so if you remember, the filter efficiency is referring to a water basis. So that's our equation mu at the top. And then the second part of the question is asking, okay, what is the minimum number of filters required by the plant? Okay, so we have to figure out how many filters does it take to operate this plant properly, given the fact that sometimes the filters are going to be down for cleaning. Okay. And so the other equation that we looked at last time was the REF, the effective loading rate, and we've got the equation up there. All right, so I'm going to give you a few minutes to work on that and see if you can get an answer for part B. Get an answer? Okay, so for part B here, say what is the minimum number of filters required? So I'm just going to write that as number filters question mark. Well, we have that total flow, and we can relate that to the effective loading rate. So we'll need to solve for the effective loading rate, and we can relate it in the sense that essentially any of the flows we have, anytime we have a flow, we can describe that as, so this is cubic meters per second, let's say, this will be convenient units. We can describe that as a loading rate times the surface area that we're loading. So in that sense, if a loading rate is just the velocity, let's say that's the loading rate itself, and then we have some area, length times width, so this is area of the bed or the filter. In order to know the amount of flow, we just take the speed of the flow through that, multiply it by the area, because this is in meters per second. Then the Q here for this one filter would be VA times that area of the filter, right? Because that translates us to cubic meters per second instead of meters per second. So we can do the same thing for the total flow, assuming we have a way to account for the downtime of the filters, right? And the downtime of the filters is captured if we use that effective loading rate, REF, where that is the volume produced minus the volume used for rinsing, minus the volume used for backwashing, all that divided by the area of the filter times the total cycle time, right? So that was our effective loading rate, and that accounts for the water lost based on using some of that produced water for these other things. And it accounts for the total cycle time that we have. If we let the filter sit there for days and days without using it and just operate it for one day of the week, then that's a very large denominator there. So we're really not having a high effective loading rate given the total cycle. Does that make sense? So that time is really important there. So anyway, this is our equation here, and we can calculate that based on the numbers we had last time, which was like 29,000 or 27,000. And then each of these was around 300. The area of the filter was 64, and the total cycle time was 24 hours. So we'd have to put that into seconds. But when we do, if we do all that, it should come out to 0.00526. That's what I got in Excel. .526 meters per second. And now if we stop for a moment and think to ourselves, we can double check this to make sure that it's in line with what we were expecting based on what the problem gave us, which was some loading rate, and that was 5.5 liters per square meter per second, or 0.0055. That's our VA here. So our effective loading rate should be less than that, right? Because it's less efficient than how much water is being put on it during production, essentially. So this is less than the 0.0055 meters per second. So that's good. We can say that it actually should be fairly close to it, but less than. So we're good. Okay, so with that, then we can come back to that concept of looking at our flow and say, we can look at it like a flux times area. So in this case, we'll say Q total is going to be equal to that flux, which is our effective, times the area of one filter times the number of filters we have. Okay, does that make sense? Because that's going to give us the total surface area of filter beds for the entire plant. And that's what really matters here. Okay, so then we just solve that equation for that number of filters, and we can say that's going to be equal to the Q total divided by REF times that area of the filter. And that's again, this time, since we multiply the area of one filter times the number of individual filters, this is still just the area of one filter. Okay, with that, then we get an answer. The number of filters, if we crunch those numbers, was the raw number was 7.13 that we would need. But we're not going to install 0.13 of a filter, right? So here we have to round up because the 7 filters is not sufficient, right? So this is a case where we're not going to put in a 3 by 3 square meter or 3 by 3 meter filter to account for that 0.13 extra that we need. Instead, we're going to install a completely, one additional filter. So we have to round this up to 8 filters in order to satisfy the design criteria. Okay, which means we actually have some extra operating space. We could expand the flow a little bit. We could have a little bit longer maintenance periods if we needed to, something like that. And so it's probably a good thing overall to have that. Okay, does that make sense? Any issues? Okay.
What's Q total?
Q total was given to us, sorry about that, it's 2.4 cubic meters per second. That's that's the flow rate that the plant needs to achieve. Thank you, that's a good clarification. So then this problem here would be 2.4 cubic meters per second divided by that 0.00526 times the 64. That's meters per second and square meters. Okay, so that is actually a pretty good segue into membrane filtration when we take a look at these filters in terms of flux, which is why I started introducing that term here, because it is a flux. A flux is a speed at which something is going through some given area, or some amount of water going through some area. Okay, just a quick reminder, please do make sure you do a reading on this. I'll either post a Moodle quiz or we'll just have a kind of in-class session at some point soon, kind of covering this cryptosporidium outbreak. I think I talked about it before and it is definitely posted to Moodle, so take a look if you have not. We'll get to that before too long. Okay, so that's it for the granular filtration, and I will now move to membrane filtration. Okay, so we talked about this already. Essentially, we were defining the difference between a granular filter bed that has some sort of a packed bed with media in it, and the particles are going to get stuck there. But it's not necessarily size exclusion. It's more like just a lot of space for stuff to settle in and get caught in various fizzy-zorb sort of a situation. If we add the Brita filter, maybe we can get some chemicals to absorb, so activated carbon kind of stuff, but still not direct filtration in the sense of like size exclusion. So membranes then are more like our size exclusion, where as water is going through, the particle gets stuck and just physically can't get through the membrane. And so a membrane is some sort of an object, so to define it, It's typically a flat sheet. So if we take a piece of paper, for example, you could consider a sheet of paper a lot like a flat sheet membrane, where if we define a membrane as a thin, sort of thin sheet or thin film here, so if we look at that definition, it says a thin, soft, pliable sheet or layer, especially of animal or plant origin, or a piece of parchment forming part of a roll. So a piece of paper then, it's filtering out some of the light, but not all the light. So you could see some light through it. I was going to put it up here, which is not going to make any sense, right? Light's going the wrong way. And maybe you could let water pass through it if you put water on it. You could probably press water through it, so it could maybe act as a membrane. I think it would start dissolving in addition, so that would be a problem, right? But if it didn't dissolve, then it might actually function like a membrane. And if like a coffee filter is a lot like that, and you're going to keep the coffee grounds, and you can push the water through it. So what do we use it for? Typically particle removal, including down to colloidal particles, viruses. And if we go far enough, we can actually start removing large chemicals, and ultimately even small chemicals with what we call reverse osmosis. Now, when we get down that far, it's not quite as much technical size exclusion as it gets into some more of the other sort of physics of individual ions and how likely are they to interact with the membrane material and stuff like that. But we can sort of think about it as size removal. It's at least analogous. So for most of the stuff, it's basically depending on how small our pores are, the spaces which water can flow through, that pore size is going to dictate what type of stuff can we remove, which is pretty obvious, right? So in a sense, membranes are relatively new technologies for water treatment. First uses were about 60 years ago for any type of water treatment, but they really became more common about 30 or so years ago. So it's a little bit younger of a technology, certainly by now pretty well developed, but it's kind of interesting to think that, it seems kind of simple. Oh, you just push water through and not let the particles out, right? You'd think that would probably be one of the first things, but actually chlorination has been used for a lot longer. Okay, so one of the things I was just talking about, these pore sizes. The smaller the pore size, the more pressure you have to push to get the water through, which is kind of obvious. So that's proportional to pore sizes are proportional to the pressure, but inversely. So the smaller the pore size, the more pressure you have to have. And a few terms to define as we talk about it. Talk about membranes. The permeate is pretty much what it sounds like. It's the water that has permeated through the membrane. We often talk about permeability. That's how permeable. That's how much pore space essentially there is for water to go through. It's not the pore size, but it's like how likely or what ease of access does the water have to move through the membrane. We can actually use similar terminology for granular media. So if you've taken, if you have not yet, you will eventually take kind of soils or that hydrology, talking about flow through porous media for groundwater. You'll see permeability for soil particles, right? So it's kind of talking about flow through pores, either in a membrane or in some granular matrix. Okay, so then we'll have a feed. So typically, when we're talking about operation, when we say permeate, really we're talking about if we have some sort of a membrane and we have flow going to it and some through it, then this would be the permeate. And of course, then a feed flow would be the water that we are feeding to the membrane to the water that we want to clean but is currently dirty, right? So that would be our definition there. Okay, then we have one other flow that is possible. We don't always operate membranes this way, but we typically do if we are kind of doing a large continuous treatment system. And that would be that we also have a concentrate or a retentate flow. So, or sometimes we would call it a rejectate. So let's say concentrate or retentate. So this is the flow that contains whatever particles were separated. So if the flow goes to the membrane and some water makes it through it, we oftentimes like to have a little bit of flow going away just to the side to carry all the particles that were removed from the membrane away from the membrane. So we automatically get sort of a waste flow. Typically it's waste. If you're talking about concentrating orange juice so that you can ship all the good tasty juices, bottle it up and ship it so that somebody at a local place can fill it with some water and then sell it to people, that whole shipping process is a lot cheaper when you're not shipping a whole bunch of water, right? So you just extract out the water by making a concentrate with a membrane, very likely. So you get some sort of permeate, and then in the store you see, oh, it's from concentrate, or it's not from concentrate, or whatever. This is just what it's talking about. So the reason why maybe you would say you would want not from concentrate is because maybe you lose a little bit of the flavors or something into the permeate, but theoretically you're capturing just about everything and retaining that, and then just diluting it again later. So occasionally that's not waste, and that's not exactly water treatment, but it's the same technologies, giving us an example of that maybe you can maybe stick to your mind a little bit, say, oh, that's the concentrate, right? You're concentrating the stuff, right? All these colloidal particles or whatever. Okay, so those are the three flows. Sometimes we operate in what we call dead end mode. And this is more like laboratory scale. I'll show you some pictures where we just don't bother with the concentrate and we let particles just start covering the membrane, and we just have some limitation because the particles will eventually clog it up too much. Okay, we're going to start with the typical, what I'll call cross-flow filtration. So this is for larger scale operation, continuous operation, so not that lab scale. We'll come back to that. So typically when we operate a membrane, like I mentioned, we want our feed flow that we need to treat coming in. We call it cross flow because what we'll essentially do is we will make some sort of a chamber like this, and we will pressurize that chamber. So I'm just going to say we'll add pressure to the chamber, usually by restricting this flow. So maybe we only let a little bit out there, force it all through a small space, or have some valve downstream at some point to give it just a very narrow escape to cause pressure, right? Because if we're putting a lot of flow going into it, we put a lot of like a big pump here, pressurizing it that way, then the water is trying to go somewhere. There's a lot of resistance. We can control with some sort of a valve to go out this retentate, which pushes water through the membrane and out our permeate. Right, so that's kind of the general design typically for a membrane filtration unit that's operating in crossflow. So the water only has two places to go, and we basically design it so that passing through the membrane is attractive enough for the water so that we get the type of rejection that we want, while having some flow to carry away all these particles. So otherwise they'll all get stuck everywhere and they'll start making their way into the pores and just clog the whole thing, or maybe make a big cake layer here and just clog it all up. Which that's going to happen to an extent, and that's largely what our membrane routine operation consists of is, okay, how often are we backwashing? What's that cycle like? What kind of membranes can we use so that they can withstand, maybe more intense backwashing or whatever. Okay, so just a quick note on drawing these as a diagram here. So I have two little diagrams. One would be the dead end filter. If we have some sort of filter at the bottom of this container, maybe this is a syringe filter or something, and we have some liquid, we are applying the feed here, and then we get the permeate here. So this would be a pretty typical way to draw a dead end filter. So again, we'll come back to that. But this one up here, I'm drawing this little box diagram to show you something that obviously this is going to be the feed. Okay. Now, typically when we draw a box diagram like this, we will draw a diagonal line somewhere on here to distinguish between the permeate and the concentrate. Okay. And it's often pretty arbitrary, or at least I'm pretty arbitrary with it. Maybe there's a convention that I'm not aware of, but you'll often see me, like, let's say, just draw a diagonal like that. Okay. So you have to stop and think about for a second, if water is flowing through here and this is a membrane, which way can it go? Like, is this the permeate or retentate? Like these two in particular. It's kind of obvious that if we do have a diagonal, this is going to be retentate, right? We were kind of sure that was going to be. But these two arrows you can also draw, and one of them is going to be the retentate. I'm sorry, I wrote that completely backwards. This is the permeate. I guess should stop me. Permeate. This one was obviously going to be the permeate because it has to pass through the diagonal either way. So if we draw it this way or if we draw it this way, doesn't matter. The flow has to cross it in order to get to that side, right? So I'll leave it how I started. Okay. Hopefully I can say this without further confusion. So you just have to essentially follow where it can go to get to that line, right? So this would then have to be the retentate on top, the way I've drawn it with the diagonal from the bottom left to the top right. So this would be the concentrate or retentate. And then essentially we just have two arrows that count as the permeate. So either we could just erase one altogether and we're good, or maybe we just draw, okay, this is the same thing. This is also permeate. Usually we wouldn't physically have two different nozzles for the permeate. You could, maybe you want to split the flow or something. But if you just draw a generic box diagram, I just wanted to distinguish there that we can flip. If we flip the diagonal, you want to follow where the flow goes, as if it's crossing through a membrane right there to get to the other side. In reality, this would be in some sort of a three-dimensional configuration, but 2D is fine, right? Okay, so that's kind of the gist of it for kind of how we draw, how we describe our membrane systems. Guess I'm slightly ahead of myself here. So we have this dead end and the cross flow. The dead end is essentially like a batch system. And here we see a syringe filter on a syringe. If you've ever used one of these in a lab, especially if you've got some dirty water, you'll recognize pretty quickly that after filtering several milliliters of water, it starts to get difficult. And eventually you might get to a point where you feel like either your thumb is going to break or the syringe is going to break, and maybe you burst the filter off the end and spray your dirty water everywhere, or you break the syringe. Yes, speaking from some experience here. So you'll recognize pretty quickly that, okay, well, there's an issue with clogging filters. Fouling is the technical term. that we might need to deal with. And there's a limit to how much filtration you can do with a given filter if you've got fouling going on, right? And there's a pressure increase, and at some point, something in your system will probably fail. If you had an enormous source of pressure and a chamber that was really robust and kept the membrane there, the membrane itself would eventually tear and just break apart and let all the water through. Okay, so there are practical limitations to that. So that's kind of what I wanted to say about that. So this dead end versus cross flow. Typically, dead end is sort of a lab scale batch process. It doesn't have to be, but that's typical. Okay, I can imagine maybe something like the orange juice example. Maybe they do batches of stuff, and they would say, okay, this is batch number 5394A, and they did it all in one batch and then cleaned a filter or something. I don't know. Maybe that would make sense. I would bet they would use a cross flow of some sort. And again, it wouldn't actually matter. You could draw it for our diagram. You could put a diagonal for the dead end if you wanted to make it look more like our cross flow, and just water has to cross that permeation, that boundary, right? I usually would just draw a filter down here, but you could do that if you wanted to. Either way, whereas a filter here, it wouldn't really make sense to draw it straight up and down, because then anything on the other side would be the permeate. I guess maybe you could draw it this way. We just don't typically do so. So normally we'll have a diagonal there. Okay, so a couple more examples here. Another common laboratory setup would be to have one of these beaker supported filters where you have this sort of a glass frit that is a support for a membrane. So you put a membrane here on top, and that's just going to be your source there. And then we'll fill this with water. So we've got water in here, or whatever liquid you're filtering. And then you apply a vacuum here to pull the air to create pressure. So therefore, in addition to the little bit of gravity pressure we now have much more pressure. And so essentially we have permeate that falls through and is collected in some beaker down here. And we've got a feed. So one thing to keep in mind here with a system like this, or even with the syringe filters, is sometimes you might actually want to keep some amount of your feed. So if we do this filtration, we have the filter, and then sometime later, we have just a little bit of water remaining, we could keep that as a concentrated solution of stuff. So in laboratory things, maybe that's actually really helpful if you're trying to, let's say, concentrate some bacteria or something to study. Maybe you do want to filter some of the water through, concentrate your analyte, and then do whatever measurements or something. And the permeate itself is what's going to waste. So you can, even though we don't have a retentate flow or a concentrate flow, we can take a concentrate if we don't filter everything. So if we stop filtration, we can get a scenario where we have concentrated our stuff. And then the amount we've concentrated, it depends a little bit on how well it's rejecting the stuff. So maybe we're concentrating algae cells to study. And then our membrane is small enough where if it rejects every single algae cell, then all we have to do is just a simple mass balance on, okay, what was the initial volume and now what's the final volume with the same number of cells in it. Okay, then we have a new concentration. Now, if it's only halfway effective, then we have a different mass balance to do, because then we have to say, oh, well, some of that concentration is leaving in the permeate, but not all of it. So we've had some concentration, but not all. So we can do a bit of a mass balance analysis. I think I've got an example for that, but just something to keep in mind. If we have continuous flow, it's very similar. We obviously had that concentrated flow line in a similar mass balance situation. But just wanted to point out that sometimes in a lab setting, we will concentrate something in a batch sort of a scheme. And it's not a flow rate, but but we can do that. Okay, so what does it look like in a lab scale for a cross-flow filtration? Well, here we have an apparatus where we have some water that we're trying to treat here. So this would be our feed. Okay, so this is feeding water up through this tube, and it's coming up here, and then our membrane is housed in a cylinder here. So we've got a cylindrical membrane. We'll talk about this in a moment, but essentially what's happening is it's operating inside out, meaning that water is coming into this tube. So water is going into the tube and then pressurized on the other side, so that some of it's forced out of this membrane. So it's kind of a cylindrical membrane here. And so whatever water makes its way out of the sides of this membrane is permeating through, and it's captured in a larger clear plastic cylinder you see there, and it's collected. So it makes its way out of the membrane, whichever way, and then it's collected, and you can kind of see this this clear plastic tube there, just outside of that darker plastic membrane, or whatever material, and then it's collected into this chamber and ultimately flows through to the permeate, just labeled nicely. And you see that's pretty clear. That's our cleaner water. It's obviously cleaner because it's removing whatever orange junk this is. So that's how this is operating. And you see over here, we've got a pump in the background that's applying the pressure. So that's pressurizing our feed. We're applying it here. We have a valve here to restrict the flow of the concentrate, because otherwise water could just flow straight through here. It's like, I don't feel like going through the membrane, I'll just go straight out here, right? That would be its normal way of doing it, but that valve is going to restrict the flow, resulting in a pressure in this chamber. So we've essentially got pressurization technically all throughout here, right? This is the pressurization zone. So we could put a pressure meter at any point in there, and then we should have higher pressure over here before we see the membrane. Some of the pressure is released by water going through the membrane, so we get a pressure drop, and then we could have a pressure valve on the other side, and ultimately we have that water coming through. Okay, so then this would be on this side, the concentrate or retentate. And if you look closely, maybe that looks dirtier than the water on the right. Kind of hard to tell, different volumes, but certainly looks pretty dirty. So could be believable. And given how clean the permeate looks, I would believe it. Okay, does that make sense? All right. So let's get into how membranes are actually designed. And then we'll talk about what they look like in practice. So mentioned already, design parameters really depend on the contaminant size that we're looking for, right? So if we need to remove viruses, then we're going to try and get a pore size that is small enough to prevent virus passage through the membrane. So that contaminant size then is going to, that's dictating the pore size, which then dictates what kind of pressure do we need. because if we've got really fine pores, then we need high pressure, which tells us we need to have a membrane system that's capable of withstanding that type of pressure. Okay, so there's several things going on based on our target contaminant. So we have operational pressure then and operational flux as both important, and these two are also related. This is what I was meaning earlier when I said that I think I was relating the pore size to the pressure or to the flux. But essentially, you're going to have more pressure required to go through smaller areas, but you're also going to have reduced flux. It just, not only is it requiring more pressure, but less water comes through, or it comes through at a lesser rate. Okay, I mentioned flux earlier. So flux we can define as a flow per area, just as we talked about the granular filtration. So ultimately this is in meters per second, or some distance per time, or a little more commonly, we'll have cubic meters per square meter per second or something. Like you see here, it doesn't have to be seconds. We could use hours, whatever time. This is a flux is going to be over some time how much volume goes through some given surface area. So that means the surface area is pretty important, right? If we want to expand our membrane operation, we simply need more membrane surface area, and that will expand our production. Operational pressure, we will often use what we would call transmembrane pressure. There's several different pressure terms. I kind of hinted at that a moment ago in terms of, okay, what's the pressure before the membrane? What's the pressure drop after the membrane? That kind of stuff. Transmembrane pressure is really that difference in pressure. That's the feed versus the permeate. So this would be pressure in the feed minus pressure in the permeate. That's the driving force giving us that effort to have water go through the membrane. Okay, so we've seen this graphic before, or something similar to it, when we were talking about granular filtration and what kind of particles to sediment or remove. And here we have at the top different separation processes. So the conventional filtration media, the effective pore size in terms of stuff that we could reject physically by size exclusion. The granular media typically have pore sizes on the scale of tens to maybe 100 micrometers. So maybe as low as several micrometers. So really not enough to get bacteria, if bacteria are typically on the scale of up to 1-ish micrometer. So you see here, bacteria, okay, yeah, maybe we can get some of them, larger ones, but definitely we're not getting all the bacteria by granular filtration. In fact, most granular filtration won't do a good job at it at all. But if we look at the operating pressure, here we have 10 kilopascals, and we get a hydraulic flux. This is liters per square meter per hour. We could go back and look at our typical loading rates for granular filtration, and that should line up decently well. If we were to do the unit conversions, this would be maybe thousands of liters per square meter per hour. We looked at liters per square meter per second, so we could do that conversion, but should line up. So if we take a look at that, we already talked about kind of what stuff we can remove. Some of the clay particles with some destabilization works great for the granular filtration. But if we want to start removing bacteria with confidence and viruses and stuff, we really have to get to filtration with membranes. And so here, microfiltration membranes are kind of the first option. Most of them will take care of bacteria. If we, let's say, use a 0.45 micrometer filter, something like this. That should usually take care of just about all the bacteria. If we go beyond that, we can get to ultrafiltration. So then we are looking at pore sizes around the tens of nanometers typically, so 0.001 micrometers, maybe a little smaller. We call this ultrafiltration, and if you notice, we do have some overlap. So the terms are a little bit of a spectrum in terms of like what pore size we're in and what manufacturer decides to call it micro versus ultra. But generally, ultrafiltration can allow us to get down to virus removal. So ultrafiltration then is really essentially what we're going to do for most, if not all, colloidal stuff, meaning they're suspended, they're really small particles, they're pretty much never going to settle. That's what we'd call a colloid, like viruses or maybe some of the organic matter molecules, the larger ones, we can get with ultrafiltration. Now, an interesting side note to put this in perspective, so this kilopascals, 100 kilopascals, this corresponds to approximately 10 meters of water. So that would be hydraulic head, right? So if you put a column containing water and you stack it up higher and higher, that water is exerting pressure, right? It's like when you go swimming in, let's say, a swimming pool and you go to the bottom, you're feeling some pressure based on the 2 meters of water that's pushing down on you. So when you get up to 10 meters of water pushing down on you, that's enough pressure to supply an ultrafiltration membrane that's somewhere in this area and that can potentially remove most, if not all, viruses. So you definitely get all bacteria. And so this is a neat technology. There's I think it's GE made a membrane system called the Sky Hydrant, if I can spell. The Sky Hydrant is essentially an ultrafiltration membrane designed for use with elevated water sources for developing countries or maybe disaster relief scenarios where you have some way to elevate your water and to use gravity to pressurize the membrane, and you have a system in place where you can change the orientation of the flows to do a backwash every now and then. Just a manual operation where you can use just simply 10 meters worth of gravity, so 35 feet or so of elevation, to do some pretty good quality filtration. And this is, if we take a look, this means we get something like, 50 or so liters for every square meter of surface area of membrane every hour. So seems like if you can have and this, by the way, I think I might have a picture of it, but the device itself is maybe about this tall. And so if you think about that housing a membrane that's probably going to be spiral wound, we'll talk about that in a moment. There's a good chance you have several square meters of surface area there. And you can have, that means maybe hundreds of liters every hour. So a pretty decent flow rate for a system like that. Okay, if we go down to more the extreme, if we're trying to do reverse osmosis, you'll see here the scale of the operating pressure versus hydraulic flux. They're inverse, right? So we've got the low pressure, high flow up at the granular media, high pressure, low flow here for reverse osmosis, which is why when you hear people so scared about the fact that we're going to run out of water or something, well, it's not actually true. It's just going to cost more. That's the thing of it. Like, worst case scenario, we have to do more reverse osmosis. It takes a lot of infrastructure and energy costs, so it's going to be pricey, and we have the brine to deal with, which is an environmental challenge. So it's going to require more engineering and consideration to ensure wherever we're putting that brine, highly saline water is going to not impact the environment too much. So there's considerations, there's challenges, and a lot of cost involved, but ultimately to run out of water is sort of a silly notion because we are capable of doing that. It's just this 1,000 to 1 feels a lot worse than 10 to 1,000, right? Kind of a deal. Okay, and with that, with reverse osmosis, we're really getting to the point where we have membranes selective enough to get rid of those aqueous salts with the ions that we would be dealing with for that. We can also use that, and maybe we could call it nanofiltration to get rid of some of the larger metal ions. So if we really had let's say we wanted to, we could probably deal with arsenic, for example, with membranes. Usually there's cheaper ways to do that with oxidation and precipitation. But anyway, so membranes. We have a couple different materials that are common to use. One would be polymeric, so plastic, rubber. When I say polymer, it's some type of a plastic or rubber. It's a repeating structure of organic molecules that we have caused to all link up and polymerize together, and then oftentimes we cross-link them or in some other manner cause them to form really just very, very large molecules, essentially. They're all intertwined and stuck together. That's a typical plastic. So almost anywhere you look, there are polymers, right? So my bottle here is clearly polymers. Most of our clothing materials either have sort of plant-based polymer sort of stuff. The fibers can kind of be thought of that, but any sort of polyester, poly meaning that's the, polyester is a polymer, right? It's many ester molecules or monomers, we could call them, polymerized together to form that. So just basically everywhere you see it. If the paint on the wall is a latex based, that latex is a polymer, and so on. So it's kind of everywhere, and we can use polymers for membranes because we have a lot of different creative ways to structure them or to create pores in them or to cast them in a manner that they just sort of generically have pores in them. They're easy to use. Ultimately, they're oftentimes the most affordable for these reasons. But you do have limited cleaning options because you have to be careful if you're going to bleach your clothes. You're going to have to be careful if you're going to use some oxidant like that to clean a membrane. You'd like to be able to, but if it's going to damage the polymer structure itself, then you have a problem. So just a few common ones. We often will use cellulose. So it's really a plant-based sort of a thing, or we can extract it from plants. And we can do repeating chains of cellulose. We can do PVC, which is polyvinyl chloride, PMMA, which is acrylic, essentially. All sorts of other ones. And we have a lot of ability to tune the surface characteristics. So if we want a positive charge or no charge, something like that, we can actually change which material we're using, or maybe even change just the surface of it for a specific application. So there's a lot of research that goes into that in terms of okay, well, which ones prevent fouling the most, or which ones are most, give us the most permeability given a particular pore size, or just all sorts of considerations there. The other would be ceramic, and this is a bit newer even than the polymer membranes because it's only been recently, I guess, we've developed enough control over ceramic manufacturing to have really good control of the pore sizes in a ceramic material. So ceramics, you've probably taken some sort of pottery class or done some of that at some point. And it's kind of fun. You can shape it how you like it, and then you fire it. And then based on that clay structure and the air pockets and everything that form, you have some kind of a pretty solid structure that's resistant. It's not going to dissolve, which is really important, right? That's part of the firing process. But if you carefully design that, then you can use those pores as a membrane. And so there's some really high-tech stuff where you can create a very nice surface that can handle pretty high pressures because it's not going to collapse like polymers will. There are some things you can do with the polymers to get high pressure systems, but with a ceramic, you can go pretty high. You can get chemically resistant because, what's chlorine going to do to a brick, right? Typically not much, right? So if you have this ceramic type material, you can heat it, you can blast it with chemicals. So there's some advantages there that you can't get with polymeric, and this is a project that a lab mate of mine back in grad school as a master's student was working on treating. It was water that was used to capture some of the pollutants from a coal-fired power plant. So you take this flue gas and do some water stripping to get out a lot of the contaminants, and then you need to filter the water, but it's like 70 degrees Celsius. So it's very hot, would probably melt most polymers or cause problems, but you could use a ceramic membrane, so that's kind of what he was looking at. And then you have an interesting advantage there because hot water is less viscous, so you get better permeability. So it's kind of a neat project. So hot water, just as an example, from coal plant. It's called flue gas. So that was a neat thing. I don't know if the company ended up taking on that technology or what, but he was working with Georgia Power as kind of, it's almost like an internship for his research project, and I think they're intrigued by that possibility. So I wouldn't be too surprised if that type of technology is eventually adopted for that kind of application. Because otherwise you have to cool that water and you're losing some advantage for that heat if that permeability works out well. Okay, so physically, what do our membranes look like when we create them? Well, if you think about a flat sheet membrane we talked about, you could just take a piece of paper or a sheet of membrane like a piece of paper and just clamp it down in a system where you can pressurize, you can apply water, maybe into a tube here, into this little pressure chamber, and then force the water through, and then collect it on the other side, right? That would be the simplest way. It'd be a lot like our granular filtration beds. But that means for every square meter of surface area, we need a square meter of room to place this little pressure sheet, right? So people have been pretty creative and said, well, we can actually take multiple sheets, and as long as we space them properly with a little bit of really, really small plumbing, essentially, if we space them properly, then we can take them and spiral them together. And so instead of just one sheet, we could have, in this case, two, but probably more than that. And so long as we keep the flow in such a manner that once it passes across the membrane, then it is physically separated from the rest of the system, which is possible if we look closely here. Then it can wind through that spiral and into the center, and then that is our permeate in this example. So we have water applied essentially on the outside of this, so it can go through the other side, it can meet the membrane, a lot of surface area here, and it can go through, and once it passes through, it's in the other channel. It's kind of like traffic, you just have to guide the traffic in the right places. You don't let the cars go in a certain way. There's just a physical barrier there, right? So if they pass through the membrane, then they can go along their way and ultimately find their way out. So it's a little tricky or a little clever, I would say, but we can get a lot more surface area into what we would call this cartridge or spiral wound membrane. Okay, so that's pretty neat, and it gives a little bit of detail here, probably a little small to read each of the bits there, but you can see that they've got these permeable support layers that are kind of like those mesh grid stuff that will allow water to flow through between the layers, and then you have a membrane in between and a different type of material to collect the permeate or whatever and convey that through. So that whole system is pretty neat. gives us, and then this is one of the reasons why if you ever go and see membrane filters in operation, you'll often see lots of cartridges that are cylindrical. Okay, it's not just, you know, that like this. There are multiple other ones we'll see in a second, but this is a very common way to apply them. They're still technically flat sheet membranes in a sense. We've just wound them. So another possibility would be to use tubular membranes. We saw one of these in that little lab setup picture that we discussed, and essentially that one just had one tube, but here we could pack multiple tubes into a larger cylinder. So another reason we might see cylinders, where we'd have water coming in, and it's allowed to go into the inside of any one of these. So water could go into any of these columns or cylinders, and then we'd have a separation layer, and then it could go out, and if it goes through one of these tubes, then it's collected in the wider chamber, and then will find its way out because it's pressurized and it just has to find a way out. So that would be that manner, and then we have the retentate over here. And again, the simple way to operate this is to apply some sort of a valve over here to pressurize it and not let water go through easily, so it's forced to try to get out through the membrane or just a little bit of the flow coming through here. Now, when we do this, what you'll notice is like the picture isn't showing all of the plumbing, so to speak. What we would add is what's called potting. So if we pot, sort of like potting soil, you know, if we pot a membrane, we're essentially sealing off anything. We also use this in electrical work terminology when you have electrical cables going through somewhere and you need to seal it to be watertight or something. You've got a bunch of wires or tubes going through some hole in the wall or something. You pot that area around to seal it off, and so that the only thing that can go through is what's going through those tubes, right? So it's the same type of deal here. So this potting process would, on this side, prevent anything from going, you know, I'm just pretending we can kind of see through a little bit here, prevent anything from going in between or around these, so it's like sealing it off. So if you ever see that term, that's kind of what it's talking about. And in the case for membranes, it's giving us that ability to control where the flow is going. Now these membranes, by the way, we could operate it in reverse. We could do it, this is going inside out, so we have a tube, and we have water going inside, and then it's going out, and some of it's making its way through. This is the inside out. I'm just going to draw it here. Operation. But we could also do it outside in. So we could do an outside in operation. I'm just draw it here, where we have water coming to the tube, and essentially it's making its way in that way, and we've potted it such that we can collect the permeate through tubes here, and this would be permeate, and that's outside in. Okay, so whereas this would be permeated through the membrane, starting from the inside and going to the outside, we could reverse it and do outside versus, outside to in. And there's a technical reason we might want to do one or the other. And if we change that, we actually want to make sure that we change the membrane itself so that our separation layer is on the outside if we're doing outside in, so that we're not getting all the junk particles collecting on the inside of all the space in the membrane that's not actually doing the separation. And as I say that, I realize I haven't shown you yet, but typically in a membrane, let's say a tubular membrane, if we take a very close look, we'll typically have a separation layer that is very small pores, and then larger pores to let water through much easier for the rest of it. So we're going to put that separation layer on the inside or the outside based on where we're, which way we're doing the flow. I think we'll probably talk a little more about that next time since I'm dealing with these slides first. Okay, so last major application type here before we go is we basically take that tubular membrane and make them a lot smaller. And so now we have what we call hollow fibers. So it's essentially, instead of like these more rigid tubes, we just have lots of little tiny ones, and we can pack these into a column or maybe into like, sometimes you just put them in water and they're just hanging there, and then you put a vacuum on them to pull water through, and you just have all these little fibers hanging around. And as you see here, it's going to be a little bit more of a challenge to pot all this properly. It's certainly possible. You just have to make sure you get all the in-between spaces and everything and get a good seal on it. But there's methods to do that and everything. But otherwise, it works the same way. Technically, you can operate these inside out, outside in. And this is one of the more common ways these days because you just get so much surface area. If you think about how much membrane surface area, even though these are really tiny, that's actually a big advantage, right? So typically when you make something smaller dimensions, that surface area to volume ratio increases. So this is a way to really expand the surface area of the membranes, even more so than the spiral wound or the tubular, and really maximizing that membrane area that's so important for our flux in a small little box. So the question is this the most efficient? I would say it's for sure going to be the most efficient in terms of that surface area you get per chamber. In practice, it probably depends a little bit on how effective is the backwashing and stuff like that. Are there other considerations? But I think most applications that are going to use something like a microfiltration or ultrafiltration, probably using these, so that probably is overall most efficient. There may be some times where there's a reason to do something different. Okay, so next time we'll have some practice and probably dig in a little more to what's actually going on at the membrane and the fouling and some stuff like that. All right, so have a good day. See you guys on Thursday.